It is my great pleasure today to introduce Sebastian Thrun. For AI researchers, Sebastian is well known for probabilistic robotics and autonomous vehicles. His group was the first to win a DARPA Grand Challenge on this topic, and he got even more fame from leading Google's self-driving cars. He's also a founder of Udacity and of Google X. Today, Sebastian is going to teach us about the fundamentals of probability. So Sebastian, why is probability important to AI researchers?
It's one of the most fundamental concepts, and it has to do with the fact that we often don't know. So early artificial intelligence assumed you know everything, and they put all these rules together. And these machines were pretty okay, but they couldn't learn anything. And this was only when people realized that there's an ability to learn that makes people so different that the machines became really, really powerful. And the fundamental basis for ignorance, for lack of knowledge, for uncertainty, is probability. That's why probability matters for everything in artificial intelligence.
So one of the things I really like about Sebastian's presentation of probability is how he goes from basics to dependency to Bayes' rule, and from there to Bayes' nets. It makes AI seem like an extension of probability. So as you're going through this section, make sure to really understand Bayes' rule, because we'll be continuing to use it throughout the course.
So the next units will be concerned with probabilities, and particularly with structured probabilities using Bayes networks. This is some of the most involved material in this class, and since this is a Stanford level class, you'll find out that some of the quizzes are actually really hard. So as you go through the material, I hope the hardness of the quizzes won't discourage you. It'll really entice you to take a piece of paper and a pen and work them out. Let me give you a flavor of a Bayes network using an example. Suppose you find in the morning that your car won't start. Well, there's many causes why your car might not start. One is that your battery is flat. Even for a flat battery, there's multiple causes. One is just plain dead. And one is that the battery is okay, but it's not charging. The reason why a battery might not charge is that the alternator might be broken, or the fan belt might be broken. If you look at this influence diagram, also called the Bayes network, you'll find there's many different ways to explain that the car won't start. And a natural question you might have is, can we diagnose the problem? One diagnostic tool is a battery meter, which may increase or decrease your belief that the battery may cause your car failure. You might also know your battery age. Older batteries tend to go dead more often. Then there's many other ways to look at reasons why the car might not start. You might inspect the lights, the oil light, gas gauge. You might even dip into the engine to see what the oil level is with a dipstick. And all of those relate to alternative reasons why the car might not be starting, like no oil, no gas, the fuel line might be blocked, or the starter may be broken. And all of these can influence your measurements, like the oil light or the gas gauge, in different ways. For example, the battery flat will have an effect on the lights. It might have an effect on the oil light and on the gas gauge, but it won't really affect the oil you measure with a dipstick. That is affected by the actual oil level, which also affects the oil light. Gas will affect the gas gauge, and of course, without gas, the car doesn't start. So this is a complicated structure that really describes one way to understand how a car doesn't start. A car is a complex system. There's lots of variables you can't really measure immediately, and it has sensors which allow you to understand a little bit about the state of the car. What the Bayes network does, it really assists you in reasoning from observable variables like the car won't start and the value of the dipstick to hidden causes like is the fan belt broken or is the battery dead. What you have here is a Bayes network. A Bayes network is composed of nodes. These nodes correspond to events that you might or might not know. They're typically called random variables. These nodes are linked by arcs, and the arcs suggest that a child of an arc is influenced by its parent, but not in a deterministic way. It might be influenced in a probabilistic way, which means an older battery, for example, has a higher chance of causing the battery to be dead, but it's not clear that every old battery is dead. There's a total of 16 variables in this Bayes network. What the graph structure and associated probabilities specify is a huge probability distribution in the space of all of these 16 variables. If they're all binary, which we'll assume throughout this unit, they can take to the 16th different values, which is a lot. The Bayes network, as we'll find out, is a compact representation of a distribution over this very, very large joint probability distribution of all these variables. Further, once we specify the Bayes network, we can observe, for example, the car won't start. You can observe things like the oil light and the lights in the battery meter, and then compute probabilities of hypotheses like the alternator is broken, or the fan belt is broken, or the battery is dead. So in this class, we're going to talk about how to construct these Bayes network, what the semantics are, and how to reason in this Bayes network to find out about variables we can observe, like whether the fan belt is broken or not. That's an overview. Throughout this unit, I'm going to assume that every event is discrete. In fact, it's binary. We'll start with some consideration of basic probability. We work our way into some simple Bayes networks. We talk about concepts like conditional independence, and then define Bayes networks more generally, move into concepts like deseparation, and start doing parameter counts. Later on, Peter will tell you about inference in Bayes networks, so we won't do this in this class. I can't overemphasize how important this class is. Bayes networks are used extensively in almost all fields of smart computer system, in diagnostics, for prediction, for machine learning, and in fields like finance, inside Google, in robotics. Bayes networks are also the building blocks of more advanced AI techniques such as particle filters, hidden Markov models, MDPs and PALM-DPs, Kalman filters, and many others. These are words that don't sound familiar quite yet, but as you go through the class, I can promise you, you will get to know what they mean. So let's start now at the very, very basics. So let's talk about probabilities. Probabilities are the cornerstone of artificial intelligence. They are used to express uncertainty, and the management of uncertainty is really key to many, many things in AI, such as machine learning and Bayes network inference and filtering and robotics and computer vision and so on. So we're going to start with some very basic questions, and we're going to work our way up from there. Here's a coin. The coin can have heads or tails. And my question is the following. Suppose the probability for heads is 0.5. What's the probability for it coming up tails? So the right answer is a half, or 0.5, and the reason is the coin can only come up heads or tails. We know that it has to be either one. Therefore, the total probability of both coming up is 1. So if half of the probability is assigned to heads, and the other half is assigned to tail. Let me ask my next quiz. Suppose the probability of heads is a quarter, 0.25. What's the probability of tail? And the answer is 3/4. It's a loaded coin. And the reason is, well, either one will come up with a certain probability. The total of those is 1. A quarter is claimed by heads. Therefore, 3/4 remain for tail, which is the answer over here. And here's another quiz. What's the probability that the coin comes up heads, heads, heads 3 times in a row, assuming that each one of those has a probability of a half and that these coin flips are independent? And the answer is 0.125. Each head has a probability of a half. We can multiply those probabilities because they're independent events, and that gives us 1/8, or 0.125. Now let's flip the coin 4 times, and let's call XE the result of the ith coin flip. So each XI is going to be drawn from heads or tail. What's the probability that all 4 of those flips give us the same result, no matter what it is, assuming that each one of those has an identically and equal distributed probability of coming up with heads of a half? And the answer is, well, there's two ways that we can achieve this. One is all heads and one is all tails. So you already know that 4 times heads is 1/16. And we know that 4 times tail is also 1/16. These are completely independent events. The probability of either one occurring is 1/16 plus 1/16, which is 1/8, which is 0.125. So here's another one. What's the probability that within the set of 0x1, x2, x3, and x4, at least 3 or more heads? And the solution is, let's look at different sequences in which head occurs at least 3 times. It could be head, 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 in which case it comes 4 times. It could be head, 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 tail, and so on all the way to tail, head, head, head. There's 1, 2, 3, 4, 5 of those outcomes. Each of them has a 16th of probability, so it's 5 times a 16th, which is 0.3125. So we just learned a number of things. One is about complementary probability. If an event has a certain probability p, and the complementary event has a probability 1 minus p. We also learned about independence. If 2 random variables x and y are independent, which you're going to write like this, that means the probability of the joint that any 2 variables can assume is the product of the marginals. So rather than asking the question, what is the probability for any combination that these 2 coins or maybe 5 coins could have taken, we can now look at the probability of each coin individually, look at its probability, and just multiply them up. So let me ask you about dependence. Suppose we flip 2 coins. Our first coin is a fair coin, and we're going to denote the outcome by x1. So the chance of x1 coming up heads is half. But now we branch into picking a coin based on the first outcome. So if the first outcome was heads, and you pick a coin whose probability of coming up heads is going to be 0.9. The way I wrote this is by conditional probability of the second coin flip coming up heads, provided that, or given that x1, the first coin flip was heads, is 0.9. Now, the first coin flip might also come up tails, in which case I pick a very different coin. In this case, I pick a coin which with 0.8 probability will once again give me tails, conditioned on the first coin flip coming up tails. So my question for you is, what's the probability of the second coin flip coming up heads? The answer is 0.55. And the way to compute this is by the theorem of total probability. Probability of x2 equals heads. There's 2 ways I can get to this outcome. One is via this path over here, and one is via this path over here. Let me just write both of them down. So first of all, it could be the probability of x2 equals heads, given that, and now I assume, x1 was head already. Now I have to add the complementary event. Suppose x1 came up tails, then I can ask the question, what's the probability that x2 comes up heads regardless, even though x1 was tails? Plugging in the numbers gives us the following. This one over here is 0.9 times a half. The probability of tails is 0.8. Thereby, my head probability becomes 1 minus 0.8, which is 0.2. Adding all of this together gives me 0.45 plus 0.1, which is exactly 0.55. So we actually just learned some interesting lessons. Probability of any random variable y can be written as probability of y given that some other random variable x assumes value I times probability of x equals I summed over all possible outcomes I for the random variable x. This is called total probability. The second thing we learned has to do with negation of probabilities. We found that probability of not x given y is 1 minus probability of x given y. Now, you might be tempted to say, what about the probability of x given not y? Is this the same as 1 minus probability of x given y? And the answer is absolutely no. It's not the case. If you condition on something that has a a certain probability value, you can take the event you're looking at and negate this, but you can never negate your conditioning variable and assume that these values add up to 1. We assume there is sometimes sunny days and sometimes rainy days, and on day 1, which we're going to call D1, probability of sunny is 0.9. And then let's assume that a sunny day follows a sunny day with 0.8 chance, and a rainy day follows a sunny day with, well, the correct answer is 0.2, which is a negation of this event over here. A sunny day follows a rainy day with 0.6 chance, and a rainy day follows a rainy day. Please give me your number. 0.4. So what are the chances that D2 is sunny? Suppose the same dynamics apply from D2 to D3, so just replace D3 over here with D2s over here. That means the transition probabilities from one day to the next remain the same. Tell me what's the probability that D3 is sunny? So the correct answer over here is 0.78. And over here it's 0.756. To get there, let's compute this one first. Probability of D2 equals sunny. Well, we know there's a 0.9 chance it's sunny on D1, and then if it is sunny, we know it stays sunny with 0.8 chance. So we multiply these two things together, we get 0.72. We know there's a 0.1 chance of it being rainy on day 1, which is the complement. But if it's rainy, we know it switches to sunny with 0.6 chance. So you multiply these two things, you get 0.06. Adding those two up equals 0.78. Now for the next day, we know our prior for sunniness is 0.78. If it is sunny, it stays sunny with 0.8 probability. Multiplying these two things gives us 0.624. We know it's rainy with 0.22 chance, which is the complement of 0.78, but at 0.6 chance it moves to sunny. If you multiply those, it's 0.132. Adding those two things up gives us 0.756. So to some extent it's tedious to compute these values, but they can be perfectly computed as shown here. The next example is a cancer example. Suppose there's specific type cancer which exists for 1% of the population. I'm going to write this as follows. You can probably tell me now what the probability of not having this cancer is. And yes, the answer is 0.99. Let's assume there's a test for this cancer, which gives us probabilistically an answer whether we have this cancer or not. So let's say the probability of a test being positive, as indicated by this plus sign, given that we have a cancer, is 0.9. Probability of the test coming out negative, if we have the cancer, is, you name it, 0.1, which is the difference between 1 and 0.9. Let's assume the probability of the test coming out positive, given that we don't have this cancer, is 0.2. In other words, probability of the test correctly saying we don't have the cancer if we're cancer-free is 0.8. Now ultimately, I'd like to know what's the probability that I have this cancer, given that I just received a single positive test. Before I do this, please help me filling out some other probabilities that are actually important. Specifically, the joint probabilities, probability of positive test and having cancer, probability of a negative test and having cancer. And this is not a conditional anymore, it's now a joint probability. So please give me those four values over here. And here the correct answer is 0.009, which is the product of your prior 0.01 times the conditional 0.9. Over here we get 0.001, probability of a prior cancer times the 0.1. Over here we get 0.198, probability of not having cancer is 0.99 times still getting a positive reading, which is 0.2. And finally, we get 0.792, which is the probability of this guy over here and this guy over here. Now, our next quiz, I want you to fill in the probability of having cancer, given that we just received a positive test. And the correct answer is 0.043. So even though I received a positive test, my probability of having cancer is just 4.3%, which is not very much, given that the test itself was quite sensitive. It really gives me a 0.8 chance of giving a negative result if I don't have cancer. It even gives me a 0.9 chance of detecting cancer given that I have cancer. Now, how come this value is so small? Well, let's just put all the cases together. We already know that we received a positive test. Therefore, this entry over here and this entry over here are relevant. Now, the chance of having a positive test and having cancer is 0.009. Well, I might, when I receive a positive test, have cancer or not cancer. So let me just normalize by these two possible causes for the positive test, which is 0.009 plus 0.198. When I work these two things together, I get 0.009 over 0.207, which is approximately 0.043. Now, the interesting thing in this equation is that the chances of having seen a positive test result in the absence of cancers are still much, much higher than the chance of seeing a positive result in the presence of cancer. And that's because our prior for cancer is so small in the population that it's just very unlikely to have cancer. So the additional information of a positive test only raised my posterior probability to 0.043. So we just learned about what's probably the most important piece of math for this class in statistics, called Bayes' rule. It's invented by Reverend Thomas Bayes, who was a British mathematician and a Presbyterian minister in the 18th century. Bayes' rule is usually stated as follows: P of A given B, where B is the evidence and A is the variable we care about, is P of B given A times P of A over P of B. This expression is called the likelihood, this is called the prior, and this is called the marginal likelihood. The expression over here is called the posterior. The interesting thing here is the way the probabilities are reverted. Say we have evidence B, we know about B, but we really care about the variable A. So for example, B is a test result. We don't care about the test result as much as we care about the fact whether we have cancer or not. This diagnostic reasoning, which is from evidence to its causes, is turned upside down by Bayes' rule into a causal reasoning, which is, given hypothetically we knew the cause, what would be the probability of the evidence we just observed? But to correct for this inversion, we have to multiply by the prior of the cause to be the case in the first place, in this case having cancer or not, and divide it by the probability of the evidence, P of B, which often is expanded using the theorem of total probability as follows. The probability of B is the sum over all probabilities of B conditioned on A, lower caps A, times the probability of A equals lower caps A. This is total probability as we already encountered it. So let's apply this to the cancer case and say we really care about whether we have cancer, which is our cause, conditioned on the evidence that is the result of this hidden cause. In this case, a positive test result. And let's just plug in the numbers. Our likelihood is the probability of seeing a positive test result given that we have cancer, multiplied by the prior probability of having cancer, over probability of the positive test result. And that is, according to the tables we looked at before, 0.9 times a prior of 0.01 over, now we're going to expand this by over here according to total probability, which gives us 0.9 times 0.01. That's the probability of plus given that we do have cancer. So the probability of plus given that we don't have cancer is 0.2, but the prior here is 0.99. So if we plug in the numbers we know about, we get 0.009 over 0.009 plus 0.198. That is approximately 0.0434, which is the number we saw before.